All right, folks. Yesterday we were talking about composite functions. I'm not sure where we left off, whether we got through the example that I wanted to get through or not, but I want to at least show you one more. So I'm going to start with like f of x is equal to 3x, and let's just say g of x is equal to 1 over x minus 4. Okay. In this example, what I want to focus on is what the overall domain will look like. So I'm going to create this new function. We'll do it both ways. We'll do f composite g and g composite f. But my interest mainly is what does the overall new rule, what does its domain look like? Okay, so, and then maybe hopefully generate maybe a procedure for determining the domain of these things. So first thing I want to do is just identify what is the domain for f here. All real numbers. Okay, so negative infinity, positive infinity. What is the domain here for g? All real numbers except 4. So we usually, I think the best way for us to write that is this way. Okay, that's analogous to saying like all real numbers and then comma or semicolon, x cannot be 4. Sometimes you'll see it written that way, but those are the same thing. Okay, obviously likewise this could have been negative infinity to positive infinity if we want interval notation there. Okay, so those domains are going to impact how we deal with f composite g's domain or g composite f's domain. And the first thing I want you to think about, let's write down f composite g of x. Okay, and I want to draw a picture of what that really means to us. Okay, what would be the first function that you are going to plug into to start this evaluation process? G. Okay, so I think I showed you the picture yesterday. We kind of had like boxes that look like this, and I called this a machine. But this machine here is essentially the function g. So I'm going to plug x in to g, and it's going to give me an output, right? That make sense, everybody? Now that output needs to be a defined value. It needs to be from the real number line, okay? So it can't be like 1 divided by 0. It can't be an undefined value like that. And it cannot be like 3i or 5i or square root of negative 10, which would be 10i, right? Because I does not belong to the real number line. If I gave you a number line in front of you, it's essentially an x-axis, and I told you, here is 3i, go place it where it belongs on there. You can't do that. It's not one of those numbers. Does that make sense? Okay. So I need a defined output so that I can actually run that through. What would be the next function that I run it through? I run it through f, and that's going to then spit out my final output. Okay. So to get this final output, that is a real number, this x needs to be defined for g, meaning that G's domain is kind of the governing domain for f of g of x. Does that make sense for everybody? So right now, before I do anything, I know my domain for this final function is at least what I've got underlined there. Okay? Now, there might be, when we construct the final function, we might generate, if there's division or anything like that, or roots involved, we might generate something that needs to be kicked out. But this is the start, okay? So, in generating the rule, I'm going to take the x, I'm going to plug it into g, so it should give me that thing back, right? Okay, so that's that. Yesterday we kind of talked about that as being trivial, but it's going to rewrite this as f of 1 over x minus 4. Okay, so hopefully it makes sense that the only way that I can evaluate f, so if I chose 4, I would get 1 over 0, right? And then that's not something, that's undefined, so that's kind of a vacated value that does not exist, well, how would I plug that into 3x? I can't. Okay, I would not get an output back. Okay, so that's kind of the idea of why that is the governing domain right now for this composite function. So now if I go to f, this here says go to f, and where you see x, replace it with 1 over x minus 4. So I'm going to do that. Okay, so f is the 3x. So I'm going to put 3, and now instead of x, it's now 1 over x minus 4. That is simple multiplication there through fractions, so I'm just going to simplify it. So my new rule, I'm going to call it h of x just so it's easier to talk about. H of x, which was the same thing as f of g of x, is now 3 divided by x minus 4. And if I ask for the domain of that, what's the only value that we see being a problem? 4. So negative infinity to 4, union 4 to infinity. And that then matched to that function's domain right there, right? Okay. Now, those two things that I highlighted, they won't always be identical. There might be something extra that needs to be kicked out of here, depending on what that looks like. But this domain down here of h will at least start with that. Yes. Yeah, so I initially took this x, and I plug it in for that x right there, meaning that then everywhere here that I see x, I replace it with x, right? So this, and it's one, you could think about it that way, or you could think about it, okay, well, g of x is equal to that right there, right? So I'm just going to replace g of x with 1 over x minus 4. So now that there becomes my input, 1 over x minus 4. That is what goes in for that x right there. Does that make sense? And we would do that however many times we see x in that f function. Okay, so let's look at what g of f of x would look like. Okay, so again, f of x was 3x, and g of x was 1 over x minus 4. Okay, now the domain of this new function is going to first start with that domain, right? Okay, so the domain of f of x was all real numbers, correct? Okay, so I'm going to say g of f of x is now 3x, correct? And now I'm going to go to g, and wherever I see x and g, I replace it with what? 3x, right? So now it becomes 3x minus 4 on the bottom. So okay with everybody? So now the domain of g of f of x, you start with the domain of this innermost function, which was all real numbers, right? But if this is my function, my new rule, even though I start with all real numbers, what am I not allowed to have? X cannot be 4/3 because that would give me division by 0 in that new rule, right? Okay. So, like I said, this domain here, this innermost function domain right there, governs the final domain, but you might, through that substitution, generate an issue. Okay, and we got to make sure we pay attention to that. So then, if I'm putting this in interval notation, negative infinity to 4/3, union 4/3 to infinity. And we can analyze these graphically, and this is what I suggest doing if you have time. Obviously on homework and less critical situations, maybe a take-home test or something like that, when you've got the time to take and say, okay, that's the function I just generated. Can I use technology to convince myself of those domains? So if we say f of x was 3x and g of x was 1 over x minus 4, okay, those are the two individual functions, okay? Now I'm going to ask myself, well, what does, if I composite those, what does f of g of x look like? Looks like that, right? Okay. Now, is there still an issue at 4 like there was an issue here at 4? That makes sense? And really all we do, and it goes back to transformations, when I composite these two things, all I do is stretch, and when I create h of x, my new function, all I do is I stretch that blue one by a factor of 3. Okay, so if there was an asymptote at 4, when I stretch this one by a factor of 3, there's still an asymptote at 4, and that's why that domain of f of g of x had a problem at 4. Is that okay with everybody? Okay. Now, that was f of g of x. Let's go g of f of x. So it looks like that purple one. Okay. Well, if there was an asymptote here at 4 on this one, and we said that that's an undefined value, and we talked the other day, I said if I follow like my graph from the right towards 4 on the x-axis, and my y values go up there, right? And I follow from the left on my x-axis, and my y values go down there. And because my y values, as I approach 4 from both sides, because they diverge, they don't match each other, my fingers don't come together, that means that value is undefined there, right? Does that make sense? So if I was looking at like the x value of 8, okay, so if I move from the right towards 8, my y values get what looks like be close to like 0.8 or something like that, or 0.9. And if I move toward the 8, moving from the left, my y values approach the same height, right? So that means that value is defined at 8. When I go, what do we have this? We call that g of f of x, okay? Does it look like there is an asymptote at x equals 4/3? 4/3. There's an asymptote there, right? Okay. If I ask it to evaluate p of 4/3, see that it gives back infinity, which is basically saying undefined because we don't know what infinity is, right? It is an undefined value. It's actually an idea, right? It's not a number. Okay. So when you're looking at GeoGebra using GeoGebra, I don't know what Desmos does if we were to ask, let's just check, we got time. If I say like let's call it h of x is equal to, what do we have, 1 over 3x minus 4. I don't know if I can ask it h of 4/3. It will tell me undefined, okay? So GeoGebra changes it into a infinity because it's using the knowledge of an asymptote there. Desmos will actually just call it undefined. Does that make sense? Okay. Which matches what we came up with by hand. We cool with that? Usually, creating the function is not an issue for people. It's understanding the domain that poses a problem. When we deal with composite functions, and we can compose as much as we want. Okay, so I don't think I ever go over 3 with you, 3 separate functions, but right here is the f composed of g composed of h, and it wants us to work through that. So f composed with g composed with h of x. Okay, what that looks like, I've always balked at that notation. I don't like that notation. So I'm going to rewrite it as when I see f, and now the composite sign opens a parenthesis for me, and then g, and then the composite sign opens another parenthesis, and then H, and then I run into my of X, so I'll put that down too. And then I need to close my parentheses. So this parenthesis right here hasn't been closed yet, so I'll close it. And then this parenthesis here hasn't been closed yet, so I'll close it. And you might not right now see the necessity of closing parentheses like that, but it does become very important later on. Like in a calculus class, it becomes very important in understanding your computer programs that will graph these things and analyze them, that kind of stuff. Okay. So what's my innermost function? What is the function that you're going to start with here? H of X. So I'm going to rewrite everything the same as it is, except for H of X is now going to be replaced with what it was equal to, so X plus 3. And now all I need to do is close off, obviously, X plus 3 parenthesis, and then the parenthesis there to the left, G. Okay, so now what function do I go target? I'm going to go look at G now, but what am I going to plug in as my variable term or variable component inside G? X plus 3. So F stays the same. Not going to mess with that. Okay, but now inside G, where you see X, you replace that with X plus 3. So that's going to be X plus 3. So I substitute a quantity, I put in parentheses, to the 10th, right? Does that make sense to everybody? Okay. So now I've got my input that I'm going to take into F, right? So everywhere in F that I see an X, I'm going to replace it with X plus 3 to the 10th. So I'll have X plus 3 to the 10th over X plus 3 to the 10th plus 1. That's my new rule. Okay? I'm just going to call that like N of X. N for new. Okay, so it's my new rule, right? You're cool with that? Let's talk about its domain. How does the domain have to operate here? First of all, what is the domain for H? All real numbers. And the reason I got to figure that out is because the domain of N is only going to work or exist when the domain of these innermost functions exists, right? Okay? So instead in the last one we only had two functions, F and G, so I only had to look at the innermost function. But now I've got two inside functions, right? So one, I need the domain to exist for H, but then I need it to also exist for G. But nice thing here about G is that what's the domain for G? All real numbers. Okay? So if there were any issues with either of those issues would reside in my new domain down here as well. Does that make sense? So if, for instance, like, let's say for some reason, like, X could not be like 5 there, and X could not be like 7 there, then in my new domain, I better not use 5 and 7. Those have to be removed, right? Because in both of these, in one of those iterations of evaluating H or evaluating G, 5 or 7 would give an undefined output back, and then I wouldn't have anything to put into F. Okay? But since they're all real numbers, no issues. Now, what is the issue here? -1. Okay? So all real numbers, but X cannot be -1. Okay. Now, does that overall function really matter? Does that domain really matter? No, it's the innermost functions domains that matter for determining this one's domain. Okay. And now this gets kind of messy. There may, just depending on what this thing looks like. Okay. Let me expand that for you. We could do binomial expansion. You guys remember Pascal's triangle last year? Okay. But even going up to the 10th row, just writing Pascal's triangle will be kind of a pain in the butt. We can expand that. If I type in expand x plus 3 to the 10th, okay, so Pascal's triangle, the 10th row, actually be the 11th row, has coefficients of 1, 30, 405, 32, 40, 17,010, 61,236. So I'm not going to read all these, but gives me those, right? So that's what that thing actually expands to if we were actually to FOIL it all out. It's pretty nasty, right? Okay. Now my denominator would be that plus 1, right? So really my denominator is just going to be that whole thing, but that's going to be 59,050. Okay, so the next thing I would want to do is say, okay, well, because that's my denominator, there could be division by 0, right? Where that thing would be equal to 0. Does that make sense? Okay, so when we've done this, you guys have done this with, on the simplest level, if I've got a function like 1 over x minus 3, the simplest level here is that x minus 3 cannot be 0, right? Okay, we've also done it on the level of where I say like the denominator is like x squared, let's say plus 5x plus 6. And then that means ultimately x plus 3 and x plus 2 cannot be 0, right? Okay. Well, if my denominator is now this polynomial, this 10th degree polynomial, basically what we're going to try to do is say, well, that thing can't be 0. Okay. So what we do is say, okay, well, where is that thing 0? And it's actually the denominator cannot be 0, so I'll do something like this. Now think about what x plus 3 to the 10th would look like. And this is where learning things about transformations can help us. And learning things, now I know we haven't spent a whole lot of time on dealing with functions that have a degree higher than 2 or 3. But if I look at like x, I'm going to say x to the nth. Okay, and I'll create a slider here for this, and let's look at the n, that exponent just being an even number between 2 and 20. So we'll start at 2, make it even, so I gotta go by 2's here. Okay, so right now you can see over here the function is x squared, right? X to the 4th, x to the 6th, x to the 8th. You see that all it's doing is kind of getting narrower and narrower, and then towards the origin in these cases, it just gets flatter and flatter. Okay, so x to the 10th looks like something like that, right? What's the plus 3? Going off transformations, what's that plus 3 going to do to that x to the 10th? Move it left 3. Okay, so let's see if that happens. It was plus 3, put parentheses around there. So it looks like that, right? So now, keep that in mind, keep that, so that's what x plus 3 to the 10th looks like. So my denominator, then what's that plus 1 going to do? It's going to move it up 1. So will that bottom thing ever cross the x-axis? No. So will that bottom thing ever be 0? Will there ever be a number you can plug in that will give you that bottom to be 0? No, because that graph we just said doesn't cross the x-axis, so there are no division by 0 issues with this. Does that make sense? So my innermost functions were all real numbers, so then my new function is also going to have a domain of all real numbers, okay, even though we've got division here, right? Does that make sense? Yes. Yeah, so if x plus, so if that became minus 1, and then we would have 2 points, yes. And we can, now that's because this function is really nasty and messy. In that situation, we would use our technology to actually figure out what those points are. So we'll see if we can do that here in a moment. So let's say that we have, so let's start with h of x. h of x was x minus 3, right? F of x g of x, sorry, was x to the 10th. And then f of x was x over x plus 1. Okay. So we got that, right? Those were the three functions by themselves. Okay. So let's look at, I'm going to type in g of h first. Okay. And g of h is that. And that's the reason I want to look at that is because remember, in order to evaluate f, this needs to have no domain issues, right? The innermost function. Are there any domain issues here? No, this is like a 4th degree polynomial, or sorry, not a 10th degree polynomial, and there's no issues there. Okay, no matter what x value you want, if you want to go out to like 1,000 on the x value, you can find a y value that corresponds to it. It's just going to be a huge y value. Does that make sense? Okay, but it's defined for all x's. Okay, so then if I go f of g of h of x, excuse me, of x, it gives me that thing. And I actually had, it was x plus 3, wasn't it? Was it x plus 3 or was it x minus 3? X plus 3. So I get that graph there, okay? And you can see, hopefully, there's no, now GeoGebra doesn't put like open dots places that you could have division by 0. But based on the analysis that we did with the transformations, we know that should never be 0. So then all I'm really interested in here, are there any asymptotes, any vertical asymptotes? And there's not. Okay, so that kind of validates that we had a domain of all real numbers there for that. Okay, so now if I had something like let's say this was x minus 1. So when I have x minus 1, now we see at that negative 1 there, right? Okay, so that would have taken the function x plus 3 to the 10th, which we initially said looked like that because we had a plus 1, but now it's a minus 1, so now it crosses there at negative 4 and negative 2, right? Okay, so then when I look at p of x, okay, do you see that we have issues at negative 4 and negative 2? Because now they're asymptotes, so they were zeros on that denominator, but they become asymptotes in this rational function. So those would be domain issues that we would need to remove. We had yesterday, I just want to keep looking at some of the examples that we worked on yesterday and their domains. I think yesterday we had a function that was f of, let's scroll back up here real quick. This is the first one. F of x was root x and g of x was x squared plus 1. Okay. And we talked about yesterday how if we take those two things and we compose them, let's go f of g of x, and we get that blue curve. Okay. So that's taking g of x and plugging it into f, where I see x, and it gives me square root of x squared plus 1, right? Okay. So think about this as I ask about the domain of that blue function. Okay, if I wanted, so it was f of g of x, okay? So the domain of f, that would have been numbers bigger than 0, right? Equal to 0 or bigger than 0, okay? And for g, the domain was all real numbers, correct? Okay? So when I find f of g of x, like I said, the domain of the innermost function is the dominating domain for this new function, and they're calling h. Does that make sense? Okay. So when I go f of x squared plus 1, okay, the domain of all real numbers is what's going to dominate this f function. Does that make sense? when I look at that right there, and I look at it graphically, does it convince us that the domain is all real numbers? Okay. Now let's kind of make a twist here because of doing something. So basically what we're saying here is there's absolutely no number. Think about x squared plus 1. Because the issue in the blue function, just generating any domain of a root, is what kind of numbers? An even root. What are the domain issues when you have even roots? Where you're not allowed to take the square root of? Negative numbers, right? Is there any, can you think of any number that you can plug in to x and it become negative? Or I guess large, maybe not negative, but larger than -1? Because it'd have to be larger than -1 to give a negative underneath the radical, right? Because we have that +1 there. Okay. So are there any numbers of x that would give me a result for x squared that would be larger than -1? Or more negative than -1? It's always going to be positive, right? And no matter what number I choose, positive, negative, or 0, when I plug it in x squared, it turns into a positive or 0. So adding 1 to it is always going to keep that radicand positive, right? So I'll never, no matter what I choose on the whole real number system, I will always have a 0 or positive number here to evaluate. So there's no domain issues there. However, if I make this a -1, okay, and just look at those, so now we're seeing there we've got, comparing the x squared plus 1, x squared minus 1, now this thing crosses the x-axis, right? Okay, there's some issue there, and what we talk about then is, are there numbers, choose a number for x that's really convenient to substitute, and evaluate that. So if I choose x to be 0, what do I get underneath that radical? -1. Can I take square root of -1? No, not in the real number system I can't. Okay, so that would be a problem, right, for my new function? Okay, so if I go back to this here, so this domain here is still 0 to infinity. This domain here is still all real numbers. And when I figure out h's domain, I'm going to start with all real numbers. Okay, so its domain, I'm going to start with all real numbers. But now I'm also going to think, okay, when I generate that actual domain, x squared minus 1 cannot be 0. Okay? Well, that means that x squared cannot be 0, and that there's really a better way of doing this. X squared cannot equal 1. So then x cannot be plus or minus 1, right? So those are two situations that I've got an issue for. But even think about it this way: what if x is x allowed to be 0? No. Okay. So if you remember what we did with radicals, basically what we said is we had to have x squared minus 1 being greater than or equal to 0, right? Okay. When I do this, basically I'm giving the cutoff values. Okay, that would happen on. It happens at 0 or 1 and -1. Okay. So now I've got my x-axis broken up into 3 regions. Everything to the left of -1, everything between -1 and 1, and everything to the right of 1. Does that make sense? Okay. Some of those regions are going to give me negatives under the radical, and some are going to be positive. So if I go to the right of 1, choose like 2. 2 squared is 4 minus 1 is 3, right? Can you take square root of 3? Yeah. Go to the left of -1. Choose like 5. -5 squared is 25, right? Minus 1 is 24. Can you take square root of 24? Yeah. Now, so we said everything over here to the left of -1 is okay. Everything to the right of 1 is okay. But let's choose like a half. Plug in a half here. What do you get if you square a half? 0.25. Subtract 1 from it? -0.75. Can I take square root of a negative number? No. So 0.5 is an issue, right? Is -0.5 an issue? Is 1/4 an issue? Yeah. All the numbers that are between -1 and +1 are issues here. So if I want to figure out my domain for this new function h, start with all real numbers, but then you also have to kick out the ones that give you an issue here. So my domain would actually be -infinity up to -1. We can include -1, and we go 1 to infinity. And now if I graph that, and this is, so that process is, I think that's messy, right? That's kind of a confusing thing to do. But if I now graph that function, by itself, does that convince you that between -1 and +1, there should be no domain values or x values? Okay. One thing that this stuff is good for is, like, here's just an application. This just talks about how the radius of a balloon being filled is dependent on the volume, right? So radius is equal to a function of volume. Okay. So if I know the volume, I know the radius. Does that make sense? Okay. Well, the volume of a balloon is dependent on, or a function of, the time that a pump is on. So I'm pumping this balloon up, right? Does that make sense? Okay. Maybe we think about this as pumping up like a bladder in an air compressor, or a bladder in a tire, or something like that. Okay. Or just a party balloon. Okay. But you're pumping it up. Okay. So if radius is a function of volume, but volume is a function of how long the pump has been running, so a function of time, can't I essentially say that the radius is a function of time? That kind of makes sense on how that works? So now I can figure out for whatever reason I might need to know the radius of this balloon. Now, instead of knowing what the volume is and knowing how long the pump was running, now I can just know how long the pump is running. And that number, that time, will tell me the radius. And that's maybe a benefit of composite functions. Okay, a lot of like electrical engineering, a lot of computer engineering, a lot of mechanical engineering, you'll start to recognize that values are generated and composed with this composition of functions in a much more efficient way. Okay, so maybe in like mechanical engineering, one value inside a system gets manipulated 2, 3, 4 different times and gives me this output value, and now I use that output value as the engineer for something else. Does that make sense? I wish we had like an engineering class or robotics class or something like that. You could see some of the application of what we learn in here in those, like, programming of those things. Hey, I'm going to, just real quick, I'm going to put up a optional